Now the next example show the limit of 2n upon n plus 3 as n tends to infinity is 2. So how to show? So we have to use the definition of limit of sequence, and by this definition we have to find the value of largest n or large n. That means we have to find the least value of small n satisfying the definition. That means it is enough to show that for every epsilon greater than 0 there exists a positive integer n such that the definition of limit of sequence should be satisfied, such that 2n upon n plus 3 minus 2, the difference should be less than epsilon for every given epsilon greater than 0, and it should be true for all n greater equal the large n. That means we have to find the value of this n. Right? So this gives what it gives, 2n upon n plus 3 minus 2. So it is 2n minus 2n minus 6 upon n plus 3 less than epsilon. It should be true for all n greater equal n. That means simplify this thing, it is 6 upon n plus 3 less than epsilon. It should be true for all n greater equal n. Right? That is, it means 6 upon epsilon should be less than n plus 3 for all n greater equal capital N. It means n should be greater than 6 upon epsilon minus 3. So what the value of capital N I should choose? So the least value satisfying this is greater than this. Therefore, if we choose a positive integer n to be at least greater than 6 by epsilon minus 3, then what will happen? This difference is less than epsilon for all n greater equal capital N. That is, we can say that limit of 2n upon n plus 3 as n tends to infinity is 2. So one example for homework is there. Find positive integer n such that 1 upon square root of n plus 1 is less than 0.03, and it should be true for all n greater equal n. So try to find out. The next example for homework also. It is limit of 1 upon square root n plus 1 is 0. Try to show this. Instead of homework, take it as an assignment. Assignment 2. This is example 1, example 2, example 3. Prove that sequence has a limit or does not have a limit. The first sequence is n square upon n plus 5, and the hint is that it does not have a limit. So try to show how to show. Next, the sequence is 3n upon n plus 7 times n raised to half, and the answer is, hint is that limit is 3, and try to show. You have to find the value of the value of n, so that the definition of sequence of limit of sequence is satisfied. And the next one is (3n upon n plus 7n square), and the hint is that has no limit. So try yourself, and the answers or hint is given with this assignment. The next example. The assignment is over, and the next example is the sequence 10 raised to 7 upon n has a limit 0. So how to show? So for every epsilon greater than 0, we find positive integer n such that the absolute value of 10 raised to 7 upon n minus 0 is less than epsilon, and it should be true for all n greater or equal n. So that means 10 raised to 7 upon n should be less than epsilon for all n greater or equal n. It means n should be greater than 10 raised to 7 upon epsilon. It should be true for all n greater or equal n. So if we choose positive integer n to be greater than 10 raised to 7 upon epsilon, then the sequence Sn minus 0 is less than epsilon. It should be true for all n greater or equal n. That is, limit of 10 raised to 7 upon n as n tends to infinity is 0. Okay. The next thing is, I think it can be done as a homework. The sequence n upon 10 raised to 7 has no limit. So try to show by contradiction. On contrary, suppose it has limit and some contradiction will be there. Similarly, homework. Next, the sequence n minus 1 by n also has no limit. Then the next example, if sequence Sn is 5 raised to n upon n factorial, then show its limit is 0. So the solution is S1, the first term of the sequence will be 5 upon 1 factorial, that means 5. S2, the second term will be 5 square upon 2 factorial. And the third term will be 5 cube upon 3 factorial. The fourth term will be 5 raised to 4 upon 4 factorial. The fifth term is 5 raised to 5 upon 5 factorial. Right? it is the fifth term. The sixth term is 5 raised to 6 upon 6 factorial. So can I do something with this? So I can write it as 5 raised to 5 upon 5 factorial into 5 by 5. Into 5 by 6. Is that right? Five by 6, yes. Then S7 is 5 raised to 7 upon 7 factorial. So I can write it as 5 raised to 5 upon 5 factorial into 5 into 5 divided by 6 into 7. So it can be less equal, definitely less equal. 5 raised to 5 upon 5 factorial into 5 by 5 upon 5 into 7. So it can be less equal. 5 raised to 5 upon 5 factorial into 5 by 7. It is equal to 5 by 7. Okay. And this thing now I can change. It can be less equal. 5 raised to 5 upon 5 factorial into 5 by, no, it is equal to, yeah, no problem. Then S8, it is 5 raised to 8 upon 8 factorial. So I can write it as 5 raised to 5 upon 5 factorial into 5 into 5 into 5 upon 6 into 7 into 8. So you can write it as, this thing will be less equal, 5 raised to 5 upon 5 factorial into 5 into 5 into 5 upon 5 into 5 into 8. So this thing will be 5 raised to 5 upon 5 factorial into 5 by 8. Right. So in general, what we can say about Sn? Definitely it will be less equal 5 raised to 5 upon 5 factorial into, for S6 it is equal to 5 by 6, for S7 it is less than 5, this factor into 5 by 7, for S8 it is less than, so it is upon into 5 by n, and it is true for all n greater equal 6. Before S6 the equality is there. So thus for a given epsilon greater than 0, there exists positive integer n such that this Sn is less than epsilon for all n greater equal n. That is 5 raised to 5 upon 5 factorial into 5 by n is less than epsilon for all n greater equal n. That is what n should be chosen. So n should be greater than 5 raised to 5 upon 5 factorial into 5 upon epsilon, and then so what value of large n, the least value of small n is large n to be chosen, so that this star should be true. So thus if we choose positive integer n to be at least greater than 5 raised to 5 upon 5 factorial into 5 upon epsilon, then what we have? Star holds. So that is limit of 5 raised to n upon n factorial is 0.